Video will look at the stabilization of the monomers in polymerization reactions. And the central question here is, how do you know what mechanism can be applied to what monomer? So as we have seen in the videos before, we can choose between radical polymerizations, cationic polymerizations, and anionic polymerizations. So if we see a monomeric structure, how do you know what kind of polymerization mechanism you choose? So, for example, when we take this monomer, we just write down what will happen if one of those structures will be applied to this monomer. So if we choose a free radical polymerization, cationic or anionic, what will happen in those cases? So we look at this NO2 group, and now we have to look what will happen if we have it attack. So first we will look at just the distinction between the cationic and anionic polymerization. So, for example, when we have an initiator with a negative charge, so it looks like an anionic polymerization. This will happen, as we've seen before. It will attack here, then it flips here, and we will get the first initiation step, or the first step in the polymerization process, and we will see that the negative charge is positioned here and the initiator is here. So I draw it once again because we see now that something can take place with the charges positioned at the positions where they are positioned. So, nice language. Okay, what can happen here? We see here the negative charge and the electrons, and we see here a positive charge. So, when we look at our basic organic chemistry courses, we see that a mechanism like this can take place. We have too much electrons here, but the carbonylic, not carbonylic, but the double O of the double-bonded oxygen has the opportunity to stabilize the negative charge here. So what we then see is a monomer stabilization process. Oh, I forgot here the negative charge. So single-bonded Lewis structure, 3 lone pairs, and we see here the plus. It makes sense because the nitrogen has 1, 2, 3, 4 bonds, and then we will see that it has a positive charge with 2 negative charges. So now, and look at this arrow. So now we see here mesomeric effects takes place. So these are resonance structures. Is this good? Yes, this is quite good because it's stabilized. So when we look at the same monomer, but then with a positive charged initiator, so what will looks like a cationic polymerization, we will see that no polymerization can take place because we see that we have 2 positive charges, initiator here, negative. We see here 2 positive charges next to each other, and that is not stabilized at all. So this is not possible. So if you have to choose for this monomer between anionic or cationic, we choose, of course, for anionic polymerization. Another example. When we take, for example, a cationic initiator for cationic polymerization, and we take this monomer, NH2. Lewis structures, very important. We see this will happen in the videos before. Initiator here, and here's the positive charge, H, this. So from your basic organic chemistry courses, you see this electron pair here, this lone pair, can be donated to form here a new bond where this positive charge will be positioned on the nitrogen. So this can take place. And you will see we also have mesomeric effects. So we draw resonance structures like this. H double bound. So 1, 2, 3, 4. No charges here. Nitrogen, hydrogen, and here a positive charge. And this makes sense. So this is a good stabilization. So if you check and we have an initiator with a negative charge, same monomer, we will see nothing takes place, no polymerization, because it will hinder the stabilization, of the stabilization will hinder the polymerization. It's not stabilized at all, actually. So we get here the negative charge. This go here, this go here. Like this. So what we see is here electrons and a negative charge. We see here electrons, repulsion here, so no stabilization at all. So this is not a good idea. So for this monomer, if we have to choose between a cationic and an anionic polymerization, of course we choose for the cationic polymerization. What is very important, it's not important that you remember those monomers and the corresponding mechanism, but you have to draw those mechanisms and see for yourself what is possible or not. So, some hints for you. In organic chemistry, normally we have electrophilic aromatic substitutions or nucleophilic aromatic substitutions, you know, with the aromatics here, for example this, plus an electrophile, etc., and we get something positioned on the ring, on the auto, meta, or para place. So this concept is a little bit similar to what we have seen in the examples before in this video. So what do we see? In the first example, we had a NO2 group like this, and we call those groups electron withdrawing groups. And those groups can accept electrons and will promote the mesomeric effect, and we can draw resonance structures with that. So we saw in the example before that electron withdrawing groups can promote anionic polymerization. So if we have here a carbon with a negative charge, this can be stabilized. And if we have electron donating groups, like an H2, we have here a carbon with a positive charge. Here we have electrons that can stabilize, and we have the mesomeric effect, and it can stabilize. Electron donating groups can promote cationic polymerizations. So, for practice, look for structures what can promote anionic polymerization. So what are electron withdrawing groups and what are electron donating groups? So for example, here an ester like this, R, and here is the rest of the monomer that is an electron withdrawing group, and for example here an OH group or ether group can promote cationic polymerizations. That's an electron donating group. Okay, the first part. So we go to the second part, because now we have to look at the radical polymerization. So if you have an initiator what will yield a radical, we can do also some polymerizations. So in this example we take styrene and we have a look at this one. So where will be where will the radical attack? So we have here a position and here a position. Excuse me, styrene is of course this one, otherwise we don't have a functional group for reaction. And we have two effects now. So if the radical will attack here, this position, the radical in the mechanism will be at the end at this position and will be stabilized by the ring. So this is the mesomeric effect. But we also know that radicals are most stabilized. Radicals are most stabilized in tertiary structures. Secondary structures are also quite good for stabilizing radicals. And then primary structures. And actually primary structures don't stabilize radicals that much. So we have two effects now. So we have here an effect that will stabilize. So this is secondary, 2 carbons, so secondary. We see that the radical, if it's formed here, is stabilized by effect here and by a mesomeric effect. So how this effect is called? This is called the inductive effect. Inductive effect. So we have now two effects what will stabilize the radical. So if we draw the structure, we see that the radical will go here. The 2 electrons of those bonds will be broken and go here to form a covalent bond with the initiator, and here we form a stable radical. So initiator, stabilized radical by the inductive effect, and then stabilized by the ring, the mesomeric effect. So this is a sigma bound, and inductive effects will go through the sigma bounds for stabilization. And know this one, this is the tertiary, secondary, that are quite good structures to stabilize radicals. So in this case, when we see this, how does the stabilization takes place at the ring? So we draw here the structure, and we see here, just like in the initiating step, this radical can go here and forms a bond with one of the electrons of the double bond here. So this, and then we will leave one electron here, what will be positioned there. So H. Now we have to draw here a double bond, because one bond was already present, and we form here with this electron and this electron a new bond, a double bond. We draw the ring. Those double bonds will be maintained, and we have here the new radical. And as you have seen, you can also do it like this. And we can form here an electron, an unpaired electron, a radical, and we can do it here. So we have a quite good, so I don't draw it now, but we have a quite good stabilization by the ring. So this is very nice. Free radical polymerization for styrene is a quite good choice. So how about a cationic polymerization if we use styrene? Like this. Attack. We have the initiator. I draw it now a little bit faster. We have here the positive charge. So how do we know if the positive charge is here? So we see here 2 carbons, so this is a secondary carbon, and we also know for positive charges that tertiary structures stabilize the positive charge quite well. Secondary carbons are also quite good stabilized, and primary carbons not very good. So once we have a secondary carbon atom, the stabilization for the positive charge is quite well. This is the inductive effect. So that's one reason why we can choose for the positive charge. Second, do we have mesomeric effects? Yes, mesomeric effects because we have a ring effect. So we can draw here, those are here electrons from the double bond, those can shift to this to form a new double bond, and the positive charge is positioned here. So we can draw some resonance structures where we have here a double bond, then the ring, positive charge here, and those double bonds are maintained. And of course, as the same position with the radicals, we can also draw the positive charge here and here. So we have also two reasons why we can choose for cationic polymerizations for styrene. Very good choice. And you can expect how it goes with the anionic polymerization. Now we have a problem because anionic species and negative charges are stabilized the best on primary carbons, then secondary carbons, and tertiary carbons is not quite well. So where do we attack now? So the negative charge can attack here. So we have a polymeric species with a negative charge here, or other way around. When the initiator attacks here, we get a negative charge there. So now we have to choose, because in an inductive way of thinking, inductive effect, we should think the attack has to take place here. So the negative charge will be formed there, but then we don't have the stabilizing effect of the ring. So when we have the mesomeric effects, we should choose that the negative charge attacks here, so the negative charge at the end will position at the secondary carbon. But then we have the inductive effect, what is not promoting destabilization at all. So how do we choose? And in this position, you have